Okay, folks. How are things going? What do people think of Lab 3 so far? Tough? Thumbs down. So what many of you are discovering about Lab 3 is hardware intensive. Hardware intensive. One of the things you're likely also discovering about Lab 3 is you simply cannot get away with not doing the reading for Lab 3. You just won't get the checkpoints done in time if you don't come to the lab having done the reading and knowing where you're going to go find the demo code and how you're going to modify that demo code for that particular lab section. The reason for that is, as I've mentioned, what we try to do as we move through these labs is, as we move through the labs and towards the final projects, is step back in terms of what we give you to start with, because for the final project, of course, it's whatever you want to do. So you'll be grabbing code from all over the place. Lab 3 is the farthest that we step back in these lab assignments. So because some people have been having some trouble with Lab 3, I'm going to spend some extra time today pointing you to the relevant demo code and how you should modify it. But it's a good idea to do some of this planning before you get there. There's just a lot to get done with Lab 3 in a single lab section. Unless you do with a little bit of planning, there's plenty of time, but it can be tricky. So before I do that, though, I want to remind you of just a few things. Your lab reports for Boyd's are due on Monday. I know I reminded you of that before, but I'm just reminding you again. And I also want to remind you that your final project proposals are due for each of you a week from, well, for the Wednesday people, it would be a week from Wednesday, this previous Wednesday. For Friday people, it's a week from today. For Thursday people, it's a week from. So if you want to talk about final projects, I'm happy to do so in lab, or if you want to drop by the office, I can do it there too. If you go to, where am I? If you go to the course site and take a look at final project proposal, and this provides you an outline of what you should provide. It's not that long. It's maybe like a page in length, but we are looking for some specific things in your proposal. So just take a look at this. And as I've mentioned before, what this proposal is mostly a sanity check. We mostly just want to make sure nobody's building anything that's going to hurt anyone or burn the building down, right? So we're checking for that kind of thing. We're also, we ask for you to just provide a high-level plan for how you're going to execute the project, just to show that you've done a little bit of thought about execution. And then the other sort of sanity check that we're doing is just to make sure that the project is of approximately appropriate scope. That is to say, not so easy that you'll get it done in a week, and not so difficult that you'd have to go to 10 years of grad school to get it done. Yeah. Projects are group projects. Yeah. You're submitting it with your group. If you want to change groups for final projects, that's fine. It's rare, but you're able to do that. Yeah.
So I see that one of the things is the schematic of the hardware. So what if like part of our project proposal is designed with schematic? So it's like you don't know what the schematic is immediately during the proposal because you haven't investigated what parts are available or happened to.
So to the extent that you can, you should do those investigations before the proposal, because part of the point of the proposal is to make sure that the project's possible. So making sure that the components that you need are available would be a good thing to check before you submit the proposal. If there are aspects of your project that are not entirely fleshed out yet, which of course there will be, it's okay to represent some things as sort of black boxes on your schematic for the time being. Like you were thinking about modifying a PS4 controller, right? So you're gonna have to take apart that PS4 controller and look at the circuit board to figure out what's going on there. If for the time being you represent that as PS4 controller box with inputs and outputs, that's okay at this point. Yeah. Other questions about final project proposal stuff? Okay, so I want to get back to PID control today if there's time. If not, we'll get back to it on Monday. But just based on what I'm seeing in lab, I want to spend a little bit more time outlining lab 3. So the code that you write for lab, a lot of the difficulty associated with lab 3 comes from the external hardware. So let me just briefly remind you about the external hardware that you're going to build, or that many of you have built, and how you should go about testing this stuff. So we spent a bunch of time going through this motor driver. So I'm not going to walk through it in tremendous detail just again, but I will remind you that what we have here is an optical isolator to isolate the, wow, my glasses are foggy, to isolate the microcontroller from the motor. And about a mega ohm resistor here to control the bandwidth of that optical isolator. A bypass cap, a snubber diode, a FET that we're using to actually pulse width modulate the motor, and then a 10K resistor here just so that we don't short power to ground when we turn on that optical isolator. A lot of people have been having trouble getting this thing to work properly. So I want to just talk a little bit about debugging strategies for this circuit in particular. The first thing I'll remind you of is you should test this. You can test this circuit and you should test this circuit without the microcontroller. So the input to this circuit is a pulse width modulation signal from the PIC32. So that's going to be a square wave, 0 to 3.3 volts at 1 kilohertz with a duty cycle that you'll set. You can generate exactly that signal on the function generator. So to test this circuit, what you'll do is turn on the function generator, attach it to the scope, and you'll look at the output to the function generator, tune it so that you're creating a 1 kilohertz square wave of amplitude 0 to 3.3 volts. If you're not careful, the function generator will produce a square wave of the appropriate peak-to-peak magnitude, but centered at 0 volts instead of being DC offset to 0 to 3.3. So you have to turn the DC offset knob to move it up. You'll then drive this circuit, and you may have the whole thing set up. And if you've set it up properly, then you should be able to turn the duty cycle knob on the function generator, and your arm will go up, and then it'll go unstable and flip over. So hopefully you have a stop in place. But you should be able to control the speed of the motor by controlling the duty cycle knob. Suppose that you do that and the motor doesn't turn, right? So the next thing that you should then scope. So suppose that you've already scoped the input from the function generator, so you can see on the scope that you are sending in the appropriate pulse width modulation signal. The next place in this circuit to scope is right here. We want to see that that square wave, that pulse width modulation input from the function generator, is being appropriately translated through the optical isolator to the gate of the MOSFET. So you should see a square wave here. If you don't see a square wave here, it suggests a problem with the way that you've set up the 4N35, the optical isolator. And that's a device where it's easy to make mistakes setting that up. There's 6 pins. You have to be careful about, there's 2 powers and there's 2 grounds, right? So some of the pins are connected to ground for the microcontroller. Others of the pins are connected to, through resistors to ground for the motor. So it's easy to make mistakes setting that up. So the first place that you'll scope is here, just to make sure that this is set up properly. And you may do that before even adding any of these other elements. You'll make sure that that's set up properly. Then you'll add in the other elements and see that the motor turns. The other thing that's a good idea to do is, before you add the motor to the circuit, apply 4.5 volts across it and make sure the damn thing turns. These are super cheap motors. Some of them break. So just make sure that your motor actually turns before you plug it in. That can lead to a lot of head scratching that ends up, just we replace the motor and then it all works. Any questions about this? It's not a tremendously complicated circuit, but it's a tricky one to get right. And we've had bugs setting this thing up that's taken us a long time to track down. Yeah.
So when you apply the 4.5 volts across the meter and you shut it off, so does the power supply have the internal bias?
That's a good question. We talked last time about how, or a few times ago, when we pulse width modulate the motor, we're turning it off quickly. There's an inductor in there that doesn't like changes in current through, right? So it reverses polarity and creates a big voltage spike, which we protect our system from with the snubber diode. And the question was, if we hook up the power supply directly across it, does it have some sort of internal protection circuitry that serves the same purpose? And my answer is, I don't know for certain, but I think so. That's the best I can do. We could look at the data sheet for the power supply. Other questions about this circuit? Okay. The other piece of the other external circuit that you will build is the low pass filter into the analog to digital converter. So this is the low torque potentiometer. It's a 10K potentiometer. We set up a low pass circuit here with a cutoff frequency that you'll decide on, maybe like a kilohertz-ish, right? So if you use maybe, I don't know, like a nanofarad or something capacitor, that's probably about right. This is just a voltage follower, right? And then the output from this op amp goes directly into the analog to digital converter input. And as we talked about, this serves two purposes. It's, first of all, low pass filtering the input from the potentiometer. So if there is noise being introduced by the control lines to the motor, we're filtering out a lot of that high frequency noise. The other thing that this does is make the input to the ADC. Actually, let me just see if you guys remember this. What is the output impedance of an ideal op amp? Yeah. So we're lowering the impedance to the ADC, right? So we have, for an ideal op amp, infinite impedance on the input, so we can measure this voltage without affecting net voltage. And then we have very, very low, in an ideal op amp, 0 impedance on the output going into the ADC, which means in that, you'll remember when we looked at the ADC, the way that the ADC is working is we charge up a little capacitor, and then when you type ADC acquire, you open the switch, which locks the voltage on that capacitor, and then that voltage is digitized by the successive approximation register, that internal circuitry that includes a DAC and a comparator that does a binary search for the appropriate digitization of the voltage, right? So we like having a buffered input to the ADC because it lowers that input, allows us to charge the capacitor quickly, so that we can control the system as fast as we want to control it. The rate limiting element for our control system, the slowest part of this whole circuit, is this optical isolator. Yeah.
You said it has a DAC in the comparator. That's like every increment converts back to some analog to analog, and then if they're the same, I have to the one that use that analog.
Yeah. So here's a schematic of a successive approximation register. We have the sample and hold circuitry. So this is essentially the capacitor. This goes into one of the inputs of a comparator, and it's comparing the voltage on that capacitor to the voltage coming out of a DAC, and it's changing the voltage on that DAC and seeing how the output of the comparator toggles to do a binary search for the voltage that best matches the voltage on the capacitor that we're using to hold the. It's a op amp comparator circuit. So which is to say, yeah. So it starts with the most significant bit, and it sets the most significant bit of the DAC to 1, and says, is the output of the comparator high or low? Which is to say, is the DAC at higher voltage or is the capacitor at higher voltage? And then it says, okay, how about the next bit? I'll change that one. Is the output of the comparator high or low? So it searches through all the bits and sees how the comparator. It's doing a bunch of comparisons between the voltage coming out of the DAC and the voltage on the capacitor until it finds a voltage that best matches the voltage on the cap. The output compare register, it is not. I'll talk about that in just a second. That changes. Let's talk about the output compare registers. So the output compare registers, where am I? So this project, right? So that's the external hardware. The code that you actually write is well, it's not simple, nothing is simple, but it involves less components than a lot of your previous projects. So your code will include an interrupt service routine and some number of threads that takes user input. I incidentally have on here, in this write-up, I asked for you to display the PID control parameters to the TFT display. I thought about that a little more, and if we're controlling this in a software interface, what's the point of also displaying that stuff on the TFT? So you don't need to display this stuff on the TFT. I can update this. You can get rid of that. Since you're going to be adjusting it on some slider anyway, we're going to have input of knowledge of what it is. So you're probably still going to want a TFT thread in there for debugging purposes, but in terms of checkout, I'm going to eliminate that because it seems contrived. In any case, you will have a thread or two that takes user input and an interrupt service routine that runs at 1 kilohertz. In that interrupt service routine, you're going to read the ADC. So that's going to give you, it's a 10-bit ADC, so that's going to give you a voltage in ADC units in the range of 0 to 1023. So you're going to read the ADC. You're going to compare the value that you read from the ADC to the desired, what am I trying to say? You're going to compare the measured ADC value to the desired ADC value. When the arm is at 90 degrees, there's some ADC measurement associated with that, right? Whatever the potentiometer value is at 90 degrees. So you're going to compare where you are to where you want to be. When I say compare, I mean you're going to subtract the two, get the error. You're going to use the error the error is going to be the input to your PID controller, which converts error to a pulse width modulation duty cycle. You will take the output of that PID modulation duty cycle and update the duty cycle of the output compare module that's driving the motor. And then you'll leave the interrupt service routine and come back and do it again. This is running at 1 kilohertz, which is pretty slow, actually. So you're not super time constrained in this lab. You have what, 44,000 cycles to spend between interrupts, something like that. So you're not super time constrained. So it's going to be sample the ADC, compare the ADC value to the desired ADC value, use that difference to compute a pulse width modulation duty cycle, send that, update that duty cycle for the output compare module, leave, do it again. And in the user thread, you will be able to adjust your desired angle. So what are the relevant hardware peripherals for this lab? The ADC and the output compare module. And that's it. That's it. And the UART stuff that we've been using, right? The stuff for the Python serial interface, that kind of thing. So how to get started? Well, so we need to figure out how to set up the ADC, and we need to figure out how to set up the output compare module. To set up the ADC, I will direct you to the analog to digital converter webpage. Here's that sample and hold register. There's that cap. And take a look at the first example on this page. We spent some time a few lectures ago looking at this. I'm just reminding you folks that this is here and that this is where you find this. What happens in here is in main, we set up the ADC. So we close ADC 10. I've seen a few mistakes where people change the 10 to some other number, assuming that it's the number of the ADC input. It's always ADC. The 10 means 10 bits. It's a 10-bit ADC. So we close the ADC. We set up all these, we spent a bunch of time talking about all these configurations for the ADC, right? So we've set all these configurations in these param 1, param 2, param 3, and param 4 values. This is doing things like specifying which analog input we're going to use. In this demo code, it's set up to use analog input 11, AN11. In the interest of just getting things running, I'd recommend not changing that when you're first testing stuff, right? Just keep it on AN11, and you can look at the I/O ports page to figure out which physical pin AN11 is. I know, but this is the process. This is the process. We go to the I/O port page. you could look at the data sheet, or you could go here and you could say, okay, AN11, that's RPB13, physical pin 24. So you take your potentiometer, you plug it into pin RPB13, and then when you run that analog to digital converter code, you should be able to move the arm and see the display on the TFT change. So that's what that demo is doing. It sets up the ADC, and then in one thread, it just reads the zeroth it reads buffer element 0 from the ADC buffer, stores it in a variable called ADC9, which is an int, and then acquires the next ADC value, opens that switch again. And then it does stuff that you don't have to do, right? It converts that analog to digital converter voltage to a float and does some unit conversions from ADC units to volts or millivolts. You don't have to do that. Just read the ADC as an integer, display its value as an integer, and see that it changes as you move the arm. Yeah. Yeah. Yep. Questions about this? Okay. The other relevant hardware peripheral is the output compare module, which if we go to the time web page and scroll down a little bit, there's an output compare section with an example. This example, you can't blindly copy and paste this example. It's going to introduce errors. So you need to surgically remove the stuff that is relevant for you. So if we scroll down to main here in this example, what this is doing is, first of all, opening a timer, specifically timer 2. So timer 2 on, internal source, prescaler 1, setting its period to the whatever the value of that variable generate period is. You want a 1 kilohertz timer. So what number will you put where generate period is? $40 million divided by 40,000, yeah. Unless you still have your system overclocked, in which case you have to adjust, right? If you're still running at 60 megahertz, then it's 60,000. Okay, we open timer 2. The next thing that happens here is we open an output compare module, in particular output compare module 3. So we open output compare 3, turn it on, point it to timer 2. We open it in continue pulse mode. I mentioned in a previous lecture, this is not the mode that we want to open it in. We want to open it in PWM mode. So this value, you will change to PWM mode. How do you know how to do that? Well, we go to the course site and we open up the plib documentation. And we take a look at the output compare functions. And we take a look in particular at the open output compare functions. And this shows us all of our modes of operation. So we will put output compare module fault pin disable. That's the mode that we're going to open our output compare module in. I'll talk in a moment about what the difference is. That's the mode that we want. So when you are integrating this example with the ADC example, you'll open a timer to overflow at a kilohertz, and then you'll open an output compare module. Might as well make it output compare module 3, because that's the one in this example. You'll change that to PWM mode with fault pin disable. And then these last 2 arguments, we can again look at the plib documentation to learn what these represent. But what these last 2 arguments represent is, let's see, value 1 is the value to be stored in the OCRS secondary register. Value 2 is the value to be stored in the main register. That is to say, so what does that mean? Well, let's look at the output compare documentation again. So we'll pull up the hardware manual, go to the output compare section, and take a look at what this means. We are interested in particular in PWM mode. PWM mode. Here we are. Okay, so we're opening this in pulse width modulation mode. In PWM mode, the OCR register is a read-only slave duty cycle register, which means whatever value is stored in that OCR register represents the duty cycle for your pulse width modulation signal. If the value in that register were 40,000, you would be producing a pulse width modulation signal with a 100% duty cycle, always high. If it was 0, you'd be producing a duty cycle of 0%. If it was 20,000, you'd be producing a duty cycle of 50%. The other register, the OCRS register, is a buffer register. So when you want to change the duty cycle of the square wave, you will call a plib function that we'll look at in just a moment that changes the value of the OCRS register. And then at the next rising edge of the square wave, the value from the OCRS register is loaded into the OCR register so that for the next cycle, your square wave will have a new duty cycle. So updates on the next rising edge. And let's see, there should be a timing diagram. Yeah. So here's how this is working. When the timer overflows, the output of the pulse width modulation signal toggles high, and then it remains high until the value of the timer matches the value of the OCR register, which in this example is 2, right? So timer overflowed when it had a value of 0, the output went from low to high, and then when the value of the timer matched the value in the OCR register, on the next cycle it then toggled low again. So you can see that by changing the value of that OCR register, we're changing the duty cycle of this square wave. And by changing the period of that timer, we're changing the period of the square wave. Pulse width modulation signal has 2 degrees of freedom. There's the duty cycle and there's the period. The period is set by the timer, which you're configuring to be 1 kilohertz. The duty cycle is set by changing the value of this OCR register. In practice, you're changing the value of the OCRS register, which is then loaded in automatically each time the system goes high. And that's what this is showing in this example. Suppose that partway through this, this period, the user writes a new duty cycle to the OCRS register. Then at the next rising edge, that value is loaded into the OCR register, and you can see the duty cycle changed. So in your code, the way that you do this is, let's see, is using a plib function call that looks like this. This too is in the plib documentation, but once you, so you enter the ISR, you sample the ADC, you compute your error. That error goes into the PID controller, and out comes a pulse width modulation duty cycle, PWM on time. That's the output of the PID controller. You make that the argument to this plib function set DCOC3 PWM. That is setting the value of the OCRS register to whatever that argument is. So that then on the next rising edge of the square wave, you have a new duty cycle on your pulse width modulation signal into the motor. So you read ADC, compute error, use PID, in comes error to the PID, out comes duty cycle. Call this with the output of the PID controller. That changes the control input to the motor. Then you leave the ISR and you come back and you do it again. Is that clear? Okay. Yeah. Yes, this code.
So like when you have the like the things that get ordered together just sort of and it's like
Yes. Yes, exactly.
you could switch the place of like those.
Oh, that's a good question. I believe you could, yes, I believe you could. The other thing that I'll point out here is the next thing that happens that you will have to carry over to when you're merging these examples is the output compare modules are mapped by peripheral pin select. So in this line here, we're telling peripheral pin select, please map output compare module 3 to pin RPB9, which is in group 4. So if you run this code and you're looking for that square wave output, you would scope RPB9. Yeah, ideally. Now, is RPB9 available? Let's look. So let's look at the development board page. RPB9. That's being used by the port expander chip select. We're not using the port expander though, so you can just keep that code exactly the same and pop off the port expander chip select jumper. And then that GPIO port's available to you. Or if you want, you can open up the peripheral pin select output table. And you could find output compare 3 here and map it to any one of these IO ports. So right now it's mapped to RPB9. If you wanted, you could instead map it to A3 or B14 or B0 or B10 or whatever you wanted. Almost everything else that happens in this example is irrelevant to you. You don't need to carry it over into your project. It's in this example, we then open up a second output compare module. You only need one, so you don't need to carry this over. We open up a second timer, timer 3. You again only need one. We open up an input capture module. We don't need that either, so you don't need to carry that into your code. And yeah, so the relevant part of this demo for you all is here, where you'll set this period to 1 kilohertz. You'll change this to PWM mode, right? And in the interest of just experimenting and getting started, maybe you set this to 20,000 and this to 0, which would generate a 50% duty cycle output. And then you could scope that and say, that looks like 50%. And then maybe you make it a 10% duty cycle and say, that looks like 10% duty cycle. The other thing to be careful of with this example is if you just grab the code, including the interrupt service routine, note that this ISR is attached to the input capture module, not to the timer. So you'll set up a timer interrupt, not an input capture interrupt. Just be careful with that. This period down here. So in this example, it's just set to some constant. It's just being set to 10,000, which means this is running at what, 40 million divided by, it's running at what, 4 kilohertz? Yeah. You'll set this to 40,000 or 60,000 if you're overclocked. Yeah. 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 So on some systems, you might benefit from doing something like this. On this one, we have a PWM period of, or a PWM frequency of 1 kilohertz, which means we're toggling the motor off and on at a kilohertz. For us, we're treating, so why does the kilohertz work? The motor acts like a low pass filter. Does that sort of make intuitive sense that the motor acts as a low pass filter? You can think about this with your car too. If you go like this on the gas pedal, the car doesn't like go like that, right? It low passes your input a little bit so that you sort of, it goes to whatever the average was. The same is true of the motor. We're toggling it on and off fast enough that it isn't actually starting and stopping at that speed. It's averaging the pulse width modulation input to some average voltage. So for our system, because we're already going fast enough for the low pass elements of the motor to be smoothing out our pulse width modulation input, we don't, I should think about this more carefully. I don't think we get a tremendous benefit from having a faster frequency PWM signal. I think once we go above, the threshold where it's getting low passed anyway, if we go faster, it's still just getting low passed. If we were to go slower, we could run into problems. Because if we start getting below the cutoff frequency of the motor as a low pass, then weird stuff would start happening. It would turn on really fast and then off and then fast and then off. Yeah. So order of operations. You're going to build the mechanical stuff. You're going to build this circuit. You may start by just building this half of this circuit. You'll get the function generator to generate a 1 kilohertz square wave, 0 to 3.3 volts, and you'll scope the output of the opto-isolator and make sure you're seeing that square wave. That means your input signal is translating through the optical isolator appropriately. Then you might hook up the rest of this. Being careful with this FET. Before you hook up this MOSFET, Google labeled MOSFET schematic. Source and drain are not what you think they are. You would look at this and think, oh, that's high, that's low, that must be source, that must be drain. It's switched. This is source and that's drain. It's an easy mistake to make. And that's gate, right? So you'll set up the rest of this, and then as you play with the duty cycle and the function generator, your arm will lift and lower. Separately, and potentially in parallel, another member of your group will build this circuit and get the ADC configured on the PIC32. And then, well, first of all, you'll build this circuit and scope the output of the op amp there, move the arm, and see the output on the scope also move. And then you'll put that into the ADC input of the PIC32 using the ADC demo code, right? And make sure that you can read that in properly. The other thing that happens in the ISR that I forgot to mention is we're asking you to send two things to the DAC. One of the things that we're asking you to send to the DAC is the ADC measurement. So how much you do that? Well, you have in lab 1, we spent a lot of time figuring out how to send stuff to the DAC. In lab 1, we were sending elements from a sign table, right? We were going to get a value from a sign table, loading that into the lower 12 bits of the DAC data, and then sending that off through an SPI transmission. In this lab, instead of loading up the sign table data, you're going to load up the ADC data. Now, keep in mind, it's a 12-bit DAC, so you can put 12 bits of data into the DAC, and we have a 10-bit ADC. So you could put the 10 bits of the ADC into the least significant 10 bits of the 12-bit DAC, and you're going to get a waveform out that looks right. It's just not going to be full amplitude, right? You might consider left shifting the ADC reading by 2 bits so that you're populating the most significant 10 bits of the DAC data instead of the least significant 10 bits, and then you get more range of the output. The other thing that we're asking for you to put onto the DAC is as you, where am I going? You are using at 1 kilohertz, you are changing the duty cycle of the square wave, right? Of the pulse width modulation square wave. We're also asking for you to output this duty cycle to the DAC, but low passed a little bit. If you don't low pass it, it looks like a really scribbly mess. If you low pass it, you can actually get some meaningful information out about what the controller is doing. And you'll end up with traces that look sort of like this, where this is a grab from the oscilloscope, where at the top you're looking at the ADC output, and at the bottom you're looking at motor control. So you can see as we command the arm to different places, what is the controller doing? This is providing you a mechanism for actually debugging your controller, getting a sense of what it's doing. We asked for you to do this for the week 1 checkout because it's so useful for the week 2 checkout. When you're actually implementing the controller, it's so useful to actually be able to see what it's doing. And there's some the low pass for the motor output is done in software, and we provided you a line of code here that just does this for you. So you take that calculated duty cycle, initialize motor display to 0, right? And then every time into the ISR, you update its value with its previous value plus your calculated duty cycle minus the previous value, right, shifted by 4. That is a quick and dirty low pass filter. Yeah.
My only question with the oscilloscope, right? If you want to read both the ADC, well, the analog from the op-amp and the motor driver, wouldn't both grounds then be sourced together through the oscilloscope?
So both of these are coming out of the DAC. So this is DAC channel A, this is DAC channel B. You're taking the ADC measurement and putting it out through DAC channel A. You're taking the motor control and putting it out through DAC channel B, so that we can look at both on the scope. And they are both coming from the DAC. So both leads go to DAC ground, microcontroller ground. One of your probes is connected to the DAC A output. The other probe is connected to the DAC B output.
So instead of connecting it directly to the motor,
Yeah.
This is the value we're pushing to the motor.
Yes. Yes. Yep. By all means, yeah, sure, if you would like to. Yeah, because this is running pretty slow, so you could certainly do this in software, I believe, and it would be just fine. That'd be cool. Anything else I wanted to mention in connection to this? Any other questions about this that people are generating? Yeah. Okay. Okay. If there's no further questions, I'll get back to PID stuff with a little bit of time remaining. The other thing I suppose I'll mention is start thinking too about, we don't specify what the user interface to this project needs to look at. It's something that I'm asking you to think about. So for your desired input angle, one thing I would ask when you're thinking about your user input is, we want to be able to command instantaneous changes in desired angle. So the motor's hanging down, and we want to have it assume a value of, we want for the desired angle to be able to assume a value of 90 instantly. So please don't implement your desired angle with a slider, or implement it in a slider in such a way that you change the slider value and there's a send button, so that you can send instantaneous changes in desired motor angle. Sure, that would be fine. Or you might set up your desired angle as a text input so that the user specifies an angle by texting it in and sending it, something like that. The control gains, your proportional gain, your integral gain, and your derivative gain, those, I think maybe a slider could make sense. And implementing that a little bit earlier might make tuning your system a lot easier. It's nice to be able to, you want to be able to change your, it is extremely helpful to be able to change your controller gains without having to reprogram the PIC. It just makes the tuning process a lot smoother and faster. So you might consider doing your work in such a way that you implement some mechanism of dynamically changing your controller gains without having to reprogram with hard-coded parameters. Okay. And we haven't gotten very far in discussing the PID controller yet, but because some people are starting to get to this point, let me be slightly strategic then about the order of operations here. So suppose that you are ready to start implementing the controller. The way that I would recommend starting is start with just a proportional controller. So you enter the interrupt service routine, you take your ADC measurement, you compare that to the desired ADC measurement, the one that you would get if you were at the angle that you want to be. Compute the difference, multiply that by some constant, and whatever the output of that is, you send that as your duty cycle to the motor. And start with that constant that you multiply by being kind of low, right? If you make it, well, if you make it 0, the motor never turns on, right? If you make it modest, then for a very large error, the commanded duty cycle to the motor will still be pretty small. So the motor will see that large error and turn on a little bit and maybe weakly come up a little bit and stop. Then you could turn the gain up a little bit higher and it's going to come a little further, maybe bounce a little bit and then stop. What you'll find is you'll turn it up a little bit and a little bit and a little bit, and you'll find a point at which it comes up and goes past the desired hover angle and starts to oscillate and oscillates continuously. And when you get to that point, you've found the edge of stability. Once you find that place, you'll add just a little bit of derivative gain, And what that's going to do is allow for you to come up quickly. It'll slow you down as you approach the desired hover angle, reduce your overshoot, and stop the ringing. It won't get rid of steady state offset. To then get rid of the steady state offset, you'll add a smidge of integral gain, and that'll pull you back up to where you want to be. We're going to talk through that in a lot of detail, right? But I'm just giving you the very quick version now in the event that anyone gets to this point in lab before we have the opportunity to talk about it again. So when you start let me just repeat. When you start implementing your controller, start with just proportional gain and start with that gain low. Keep it low enough that you get large steady state error, then turn it up and turn it up and turn it up until you get oscillation, and then add a little derivative gain. Yeah. Yes, sure. Yeah, I mean, it's everything that's written here. By week 2, I am expecting closed loop control of the motor. So an implemented PID controller. Doesn't have to be tuned. Can be a lot of ringing. Can be messy. Doesn't have to have, you know, a nice user interface. But PID control. I would like in week 2 for you to be able to change proportional gain, integral gain, and derivative gain. Yeah, not necessarily angle. Yeah. I want for you to be in a position to get, yeah. Okay. Any questions?
This is just a 3-week lab, right?
What's that? This is 3 weeks. Yeah. Yeah.
Have you decided to push back weekend?
We're going to keep it the same. Once you get through week 1, week 2 becomes largely code, right? So I think we're still, if you didn't quite make the week 1 checkpoint, I think you're in a position to meet the week 2 checkpoint. because it's the week 2 is largely code stuff, which people are comfortable with at this point. There's just a lot of debugging associated with the hardware.